Hello and welcome. In this video, we're going to introduce addition rule, multiplication rule, and conditional probability. First, take a look at the addition rule. This is the formula we're going to use when dealing with addition rule. The or sign can also be write as u, this u, and n is like a n. So think about this. Flip two coins, a nickel and a dime. Let A equal to heads shows on the nickel, and let B equal to heads shows on the dime. We get the probability right here. This is also known as the sample space. Find probability of getting A or B, which is probability of getting heads shows on the nickel or on the dime. We're going to use our addition rule. We're going to first find the probability of heads shows on the nickel plus the probability of heads shows on the dime minus the probability of heads shows on both nickel and dime. So if you take a look at this Venn diagram right here, we're going to first find the probability of getting this pink circle, and then the probability of getting this blue circle, and minus the probability of the overlap section. And finally, we get 3 over 4. This is the sample space approach, which is right here. We need to explore the probability of A and B. Alternatively, the joint probability of A and B. Several different notations exist. Probability of getting A and B, or probability of AB, or probability of A and B. So just as I said before, this like n-shaped notation is n. If events A and B cannot both happen, then probability of getting A and B is 0. Then we say that events are disjoint or mutually exclusive, meaning I hate you, I hate you, you hate me, we cannot exist together. So draw one card from a standard deck. A stands for the card is a jack, and B means the card is an ACE. C means the card is a red. So if you're not familiar with a deck of cards, don't worry, I'll explain everything from zero. So basically, a standard deck has 52 cards, and I'm trying to zoom out of the screen a little bit. It's kind of hard to manipulate on my iPad. Okay. So a standard deck has 52 cards. There are 4 suits: spades, clubs, diamonds, and hearts. Each suit has 13 cards, numbers 2 through 10, plus jack, queen, king, and ace. And we defined the events already, and red cards are hearts and diamonds, so there are 26 red cards total. Now let's go step by step. First, how many jacks are there? There are 4 suits, and each suit has 1 jack. So there are 4 jacks total. Same idea for ACEs. There are also 4 ACEs. And first, finding the probability of A and B. So those are all P's. They're not showing fully. Apologize for that. So this means that what's the probability the card is both a jack and an ACE? Well, that's impossible, right? A card cannot be both at the same time. So this probability is 0. And second, let's take a look at probability of A and C. Now we want a card that is both a jack and red. There are 2 red suits, hearts and diamonds. Each has 1 jack. So there are 2 red jacks. So the probability is 2 out of 52. The probability of B and C, same idea, but now for ACEs. There are 2 red ACEs. So the probability is also 2 out of 52. And probability of A or B. Now we're looking for a card that is a jack or an ACE. There are 4 jacks and 4 ACEs, and none of them overlap. So total is 4 plus 4 equals 8. So the probability is 8 out of 52. Then let's take a look at probability of getting A or C. Now this one is important. We can use the formula, probability of A plus probability of C minus probability of A and C. Why do we subtract? Because we counted the overlap twice. So probability of A is 4 over 52, and probability of C, probability of A is 4 over 50, yes, and probability of C is 26 over 52, and probability of A and C is 2 over 52. Now plug in, then we get 28 over 52 at the end. And then probability of A or B or C. Now we combine everything. We use probability of A plus probability of B plus probability of C minus the overlaps plus any triple overlap. So 4 over 52 plus 4 over 52 plus 26 over 52 minus 0 minus 2 over 52 minus 2 over 52. There's no triple overlap here, so total becomes 30 over 52. So the key idea here are count how many cards match the condition, and then divide by 52, which is the total. Be careful with overlap when using OR. If you remember one thing, remember this. And means overlap. OR means combine, but subtract overlap. Okay, so let's keep going. The conditional probability. If you have probability learned in a rule, you have probably learned a rule for calculating probability of A and B in a previous class. You learned probability of A and B is equal to probability of A times probability of B. This is not our rule anymore. It only holds for independent events. To make probability accessible to students in earlier grades, we just assume that our events are independent. We cannot live with that simplification anymore, since many events in the real world are not independent. Our new rule for calculating the joint probability of A and B is the formula right here. And this probability of B slash A is meaning the probability of B given A has occurred. Note the difference between the rule you learned in a previous class and the new rule. This leads us to a very important conclusion. If two events are independent, then probability of B given A has occurred is equal to probability of B. And that makes sense, right? Because think about that. If B and A are independent, like totally independent to each other, then even though we add a prerequisite condition, it doesn't really matter because in any scenarios, they will always be independent to each other. Like they won't affect each other's probability. And AP Stats doesn't give us the new rule in the above form. Rather, it arranges terms to solve for the conditional probability and gives us the conditional rule for probability. And this is our conditional rule. The probability of B given A is equal to probability of A and B, which is the both, and divided by probability of A. And probability of A given B is equal to probability of A and B divided by probability of B. So you always use the both probability divided by the given. So in here, the given is A. So we divide by the probability of A. In here, the probability, the given probability is B. So we divide by the probability of B. So that's what we're doing. And let's explore conditional probability through an experience rather than the formulas. So I know like the formulas right now we've been talking about is kind of ambiguous right now. So let's make it more like touchable in real life. So this is an experiment we did on class. We assume we counted how many classmates in that classroom is. So there's total 29 people in that class, and 21 with dark hair and 8 with light hair. And out of the 21 people with dark hairs, two of them have blue eyes, and 19 of them don't have blue eyes. Out of the 8 light hair peoples, 4 of them have blue eyes and 4 of them don't have blue eyes. And we let A equal to person has dark hair and B is person has blue eyes. Then we're calculating using the formulas we just developed to help us to calculate the probability for each one. Okay, I just find out that if I zoom out a little bit, then it can show the whole picture. So yeah, so those are the P's and yeah, okay, that doesn't really matter. Okay, so probability of A, which means the probability of person has dark hair, is 21 out of 29. Probability of people has blue eyes is 6 out of 29. Because out of the 21 dark hairs, there's 2 blue eyes. Out of the 8 light hairs, there's 4 blue eyes. So 2 plus 4 is 6. Probability of A and B is probability of person has both dark hairs and blue eyes. Therefore, it's only these 2 people, so 2 out of 29. And the probability of A or B is probability of person has dark hair or the probability of person has blue eyes. So 21 people has dark hairs, 21 people have dark hairs, and 6 people have blue eyes, but there's 2 people overlapped right here. Therefore, we have to subtract 2, and we get 25 over 29. The probability of A given B is probability of person has dark hair given the person has blue eyes. Therefore, there's 6 people who have blue eyes, and out of the 6 peoples, we have 2 people have dark hairs. Therefore, we use 2 over 6. the formal ways to writing this is 2 over 29 divided by 6 over 29. But because the denominator will be cancelled at the end, so we just use 2 over 6. It doesn't matter. The probability of B given A is probability of person has blue eyes given the person has dark hair. So there are 21 people who have dark hairs, and out of the 21 people, 2 people have blue eyes. So we use 2 over 21. We get 2 over 21. Or you can write it as 2 over 29 divided by 21 over 29. Same thing as 2 over 21. So those are just some fun experiment from in-class activities using the formulas we just learned, and that's good. So are A and B independent? That's a question. So how are we going to justify that? Well, we're going to basically compare probability of A. Is it equal to the probability of A given B? Because remember the formula we just developed, which is the probability of A and probability of A given B should be equal to each other if they are independent to each other. Because if the values are equal, then even though we have a condition, it doesn't really matter because it won't change our final probability. So let's compare that first. So the probability of A is 21 over 29. The probability of A given B is 2 over 6. And change them all to decimals, we'll find out that they are not equal to each other. Therefore, we can say that it is not independent, meaning they are related to each other. Another way is that you can also use probability of B and compare it with probability of B given A. We use 6 over 29, compare with 2 over 21. Same thing, they're not equal to each other, so no, they're not independent. So 2 ways you can approach here, whether you're using probability of A or probability of B. Remember to compare with their corresponding conditions. So just don't forget the order matters in probability cases. So thank you so much for watching. I hope you have a great day.